Hi everyone, this is your host, Amir Jafari. In this series of lectures, we are going to talk about quantum field theory, one of the most important and exciting fields of modern physics, and also infamous for being difficult, among the students of physics. But we'll see how difficult it is. I'll try my best to make it as easy as possible. Okay, so let's begin our discussion, as I said, with this question. What is quantum field theory? Well, quantum field theory is the most successful theory we have right now for the combination of special relativity and quantum mechanics. You know that classical mechanics fails when you try to apply it to high speeds, near the speed of light. There you need special relativity. And also it fails when you try to apply it to subatomic particles, very small distances in space. There you need quantum mechanics. Now, if you have a particle, for example, which is small, a subatomic particle like the electron, and at the same time it moves very fast, near the speed of light, what do you need? Combination of special relativity and quantum mechanics in order to describe uh, the motion of this particle. So this is why we need this combination. Now, while you can try to, in principle, generalize the Schrodinger equation or the approach we have in ordinary non-relativistic quantum mechanics into the realm of special relativity. What's wrong with that? What's wrong with writing equations like the Schrodinger equation, but somehow relativistic equations? For example, the Klein-Gordon equation. The Klein-Gordon equation is the relativistic version of the Schrodinger equation. Instead of using the formula for kinetic energy coming from classical mechanics, in the Hamiltonian in the Schrodinger equation in an operator form, you can use the relativistic expression for the kinetic energy, for the energy of the particle, and get a new relativistic wave equation known as the Klein-Gordon equation. What's wrong with that? Why don't we do this? Well, we do this in relativistic quantum mechanics. It's called relativistic quantum mechanics because you're trying to write down wave equations, differential equations like the Schrodinger equation, but relativistic equations. But it's not successful. The reason that this approach, writing down differential equations, wave equations for wave functions give you the probability of finding the particle in a given volume of space, like the Schrodinger equation, wave function, you know, which gives you the wave function for a non-relativistic particle. This approach doesn't work when you try to combine quantum mechanics with special relativity because basically mass and energy are the same thing according to special relativity. E equals mc squared, right? This is the most famous equation in special relativity and maybe the whole physics. So um, when you write down a differential equation for the wave function, you are implicitly assuming that the type of the particle you are working with and the number of particles you are working with are fixed. When you write down the Schrodinger equation for the hydrogen atom, for two particles there, one proton, one electron, you are assuming that you have two particles to begin with, and you have two particles to end up with. The number of particles don't change. You have one proton, one electron. They can change. And the type of particles can change. You have, for example, fermions here. Okay, you don't have photons, for example, to solve an equation. So when you work with non-relativistic particles, slowly moving particles, this approach is fine. You can do it, and we do it. Quantum mechanics is very successful, and for example, when you apply it to hydrogen atom. But when your particles are relativistic, namely they move very fast near the speed of light, a new problem rises because E equals mc squared. When you have high energy particles, that energy can be converted into mass. So you start with two particles, one electron, one proton, but because these particles are energetic or moving very fast, that extra kinetic energy can be converted into mass, giving rise to new particles. So although you start with two particles, electron and proton in the hydrogen atom, but because of high energies involved, new particles can pop up all of a sudden during the experiment. So pions, mesons, positrons, photons can appear all of a sudden during an experiment, for example, in particle physics inside a collider, for example, and you cannot, describe the physics dynamics of these particles using the Schrödinger equation because that Schrödinger equation was written for just the electron and proton that you began with. Okay, so E equals mc squared, the equivalence between mass and energy, becomes a serious difficulty when you're trying to combine special relativity and quantum mechanics because it dictates that the number of particles can change and the type of particles can change. You can start with fermions, with electrons, for example, but new particles of different type can be created. For example, photons, okay, or pions, mesons, different type of particles, different form of energy can be created. So this approach of writing down differential equations for wave function for fixed number of particles uh, doesn't work in relativistic case. Now, what you need in this combination, for a successful combination of special relativity and quantum mechanics, is a mathematical tool which enables you, one, to create and annihilate particles anywhere in space and time, because new particles can be created anywhere in space and time, at any point in space and time. And also, you need, two, an operator which acts on quantum states, transforming your quantum state to another quantum state. For example, if you have one particle to begin with, you are in one particle state, quantum mechanically. Now, when there is a creation of a new particle, when a new particle is created, you are in the state of two particles. You have two particle state. When another particle is created, you jump to three particle state. When another particle is created, you jump to four particle state. So the number of particles that you are working with at any moment in time dictates a new quantum state. So by creating particles, you're jumping from old states to new states with one more particle. By annihilating particles, likewise, you are jumping from the old state to a new state with one less particle. Okay, so you need an operator mathematically in order to operate on these quantum states and shift them from one particle state to two particle state, from two particle state to one particle state, so on and so forth. So you need a mathematical formalism, which is a field, because in classical physics we have this concept of field. A field is defined at any point in space and time. You need this concept of a field to do something at any point in space and time, to create and annihilate particles at any point in space and time. So you need this concept of a field. This is familiar from classical physics because, for example, there we have scalar fields. A scalar field like temperature field in a fluid. It gives you a scalar at any point in space and time. A magnetic field gives you a vector at any point in space and time. A tensor field gives you a tensor at any point in space and time, so on and so forth. The metric tensor, for example, in general relativity is a tensor field. So you have this expression, doing something, defining something at any point in space and time, is familiar from from classical physics. It's the concept of a field, familiar to any physicist. So because you need to create and annihilate particles at any point in space and time, you need this concept of a field. Okay, and also because you are working in the context of quantum mechanics, you are jumping from one particle state to two particle state by creating a particle, or jumping from three particle state to two particle state by annihilating a particle, so on and so forth. You need an operator. The mathematical object which does both of these things together at the same time is can be called a field operator. It's a field defined at any point in space and time. It's an operator acting on quantum state. We call these quantum fields. The theory which studies these quantum fields is the quantum field theory. It's the theory of quantum fields, quantum field theory. So this is the reason we need quantum fields in order to combine special relativity and quantum mechanics, because we need this creation and annihilation, procedure, and also we need this, concept of operator by acting on, quantum states, enabling us to jump from one state to another state with one more or less particle. And when there is no particles around, we call this state the vacuum. The vacuum means there is no particle around. Okay, so if you act and operate on this state, the vacuum state, you're going to get one particle state. So you have created one particle, so on and so forth. So this should make sense, at least very in a very non-technical way. You can think about it. You can visualize it. Um, Sometimes it's useful to give, examples or analogies from classical physics. You know that in quantum, mechanics and quantum field theory in general, it's not always possible, and it's always hard, basically. Let's put it this way, to give examples from classical physics to understand something quantum mechanically, because it's a different world. But sometimes, similarities and examples work. In this case, I can give you this example. Imagine you have a swimming pool. Okay, I'm trying to give you an example in order to understand what's going on in quantum field theory, what kind of object, what kind of beast we are, dealing with. Um, Imagine you have a quiet swimming pool. There is a swimming pool. There is no one swimming. There is no wind. There is no wave on it. The surface of water is quiet. Okay, you can call this the vacuum. This is the vacuum of your state. There is nothing on the surface of water in terms of the waves, stuff like that. So we call it the vacuum. Nothing. Nothing is present. Now, imagine that there is a wave on the surface of water. You know from quantum mechanics, ordinary quantum mechanics, non-relativistic quantum mechanics, that particles are represented as waves in quantum mechanics. And the formula for that wave, de Broglie wave, if you like, is related to basically the wave function, right? Wave function gives you the probability of finding the particle at any given volume in space. So we know how to deal with waves as particles in quantum mechanics. Particles are waves, okay? Now, in your swimming pool, you have waves. Quantum mechanically, you can say that I have particles. Now, in quantum field theory, you say that no, this is not enough. This is not enough because special relativity tells us that E equals mc squared, and new particles, so new waves, can be created. How to create new waves? Well, think about it. Think about this swimming pool. Imagine there is no wave, nothing else, just a quiet swimming pool, and you want to create a wave, create a particle. What do? You drop a pebble, you drop a water droplet, you drop a little rock, and then the surface of water will be excited on the surface of water, and it gives you a wave. A wave is a particle. So quantum mechanically, you have now a particle. How you created that particle? By exciting the surface of water. The surface of water mathematically, every point, on the surface of water has a depth. That depth is a mathematical, basically field, because at any point on the surface of water, you have some depth. So you have a field. Depth of water is a field. It's a scalar field in this example, okay? So when you drop a pebble and excite some point on the surface of water, you change that depth of water, that field at that point. So you are exciting a field and you create a wave, which is a particle. So you create a particle by exciting a field. A field here, the field is the depth of water, and the wave, created this way can be interpreted as a particle. In quantum field theory, we do exactly the same. We say that when there is no particles around, we have the vacuum. The field is quiet. We are in the ground state. We are in the vacuum state. Okay. The depth of water is constant everywhere. Okay. Now you excite that field at some point in space time by giving energy, by dropping a pebble, there, and exciting that field means creation of a particle. And then you have waves, quantum mechanically waves are particles. So excitation of a quantum field is interpreted as a new particle. Now, if you have a small pebble, in the example of the swimming pool, that pebble, dropping that pebble, will excite the surface of water just a little bit, right? So it can be, it's going to create a wave, but that wave is going to represent a one particle, say, okay? But if you drop a, larger rock, you're going to have a, bigger excitation on the surface of water. And that can be interpreted as having multiple particles. You have higher energies, you have a larger number of particles, not just one. So by giving enough energy as excitation on the surface of water, you can create more and more particles. The number of particles can be increased. There is no limit for that by giving extra energy. So you are exciting the quantum field anywhere in space and time. That excitation leads to waves, and those waves are represented or interpreted as particles. That's all we have as you can call it the main idea behind quantum field theory. And this is useful in many areas of physics, not only in particle physics. We have applications, for example, especially in statistical physics. Even in fluid dynamics and turbulence theory, we have applications. The methods of quantum field theory are applicable here as well. So it's a very general framework, a very general theory. So this is a wrong impression if you think that quantum field theory is useful only in particle physics. Historically, it was developed for problems in quantum and in particle physics. But today it's used in statistical physics and different areas of physics like turbulence, etc. And we're going to talk about this because in this course I'm not going to focus primarily on particle physics because I'm not a particle physicist to begin with. We're going to have examples from statistical physics, from fluid dynamics, from theory of turbulence, problems like that. So I guess this is enough as an introduction, as a very primitive introduction. In the second lecture, we're going to refine this, picture, these concepts, what we mean by excitation, why we fail by writing equations, why we fail generalizing the Schrödinger equation to, relativistic cases, problems like this. In the third lecture, we're going to refine this picture and more and write down, equations, for example, for the quantum fields uh, and the equations governing these quantum fields. Why we have, for example, simple harmonic oscillator interpretation for these excitations, uh, which create particles. So it's stuff like this. So we were going to go into more details.